Medical University in Innsbruck. Innsbruck is famous for skiing, but today I'm talking a bit about Hadoop, our Hadoop pipelines we implemented in Innsbruck. So we heard a little bit about Hadoop these days already. So basically it's an open source framework to store and process large data sets in parallel. And for that, Hadoop is using a cluster of nodes, commodity hardware, so low budget components. The nice thing about Hadoop is that it scales with the number of nodes. And when you work with Hadoop, you have two components. First is the HDFS, the distributed file system, which is used for storage your data. It lies on top of the POSIX file system, and your data is distributed on the cluster nodes. And the second pretty famous programming model is MapReduce. MapReduce is a processing model, as I said, and it has been developed by Google in 2004. And yeah, the pretty nice thing about MapReduce is that it hides a lot of things from the programmer. So what MapReduce is doing for you is it splits your data automatically. It's doing the parallelization of your job. It handles machine failures, meaning that if one node in your cluster is going down, it automatically executes this chunk on a different node. And it also handles the machine communication, meaning that of course, this is a cluster of nodes, and sometimes the data is located on node 1, and node 2 is needing this information, and then it automatically copies the data from node 1 to node 2, for example. And as a programmer, you just get a simple API, and you have to implement two functions, the map and the reduce function. And this is, of course, dependent of your use case. It's not always that easy to implement that, but of course, here the MapReduce functions are applied to each line of your input. So all your data is located in the HDFS file system. It's the import source for MapReduce. And when you write your first program with MapReduce, you always have to implement the word count. That's the hello world of MapReduce. And what's done with this example is that you just count the words of your input. And I just want to give you a short preview. And so you have the map and the reduce function in MapReduce, and when this is your input data set, just one line here, the map normally splits your data. Here it just splits it into tokens of words, and the reducer sums up the different keys. So for example, here we have 2 times the word is in my input, and then the reducer sums up the same key. So in this example is, and then we get as an example, as a result here, the count 2 for the word is. You can write this, for example, with Java. This is the map function. This is the reduce function. And we will show tomorrow in our tutorial, in our CloudGene tutorial, how you can implement a simple MapReduce use case with Java or also with other programming languages. So, but the problem with MapReduce is that it also has limitations. So the one thing it's always a problem with MapReduce is the indexing. So you don't have selective access to your input data set. For example, if you have a VCF file, for example, you have chromosome 2 and you're only interested in one part of this chromosome 2, maybe from the beginning to position 5000, you always have to go through the complete input. And this is, of course, not always fun to do. And also it has problems with iterative algorithms, and also caching is not natively supported in MapReduce. So there's an improvement of MapReduce, Hadoop 2 or Hadoop Yarn. And with Hadoop Yarn, the nice thing is that you get other processing models beside MapReduce as well. So for example, you get Spark or you get Giraffe. And the complete Hadoop platform is not just MapReduce. The complete Hadoop platform is the HDFS, is MapReduce, but also other processing libraries, and also Apache Pig, Hive, or HBase. And here you can see in Hadoop 1, we just have the MapReduce programming library, and here in Hadoop 2, we have other data processing libraries as well. Okay, let's go to MapReduce in bioinformatics. As you can see, and we heard that today as well, there are pretty nice libraries in bioinformatics. So we are using a lot the Hadoop BAM library in Innsbruck. We're also using SEAL for data alignment, and also other applications have been published the last years. But the important question, the interesting question is this one from BioStars. I think it's quite new, this topic here. And the question is, why is Hadoop not a lot used in bioinformatics? And of course, there are two sides to this, two answers to this question. The first side says, okay, bioinformatic papers are proof of concept, and the real-world use of Hadoop is quite low. And the other side says this is the Hadoop world. It's from a talk from a guy from Cloudera, and he says genomics isn't special. You can reuse all the Hadoop stack, and you don't have to reinvent the wheel for computational biology. And of course, the truth is somewhere in between. And the more interesting question is, why are we using Hadoop in Innsbruck? And when we started Hadoop in 2010 in Innsbruck, we were looking for a scalable and affordable approach to process our NGS data. We are a really small institute in Innsbruck, and so we didn't have the money to buy a big, huge cluster. And when you have a look at the NGS data, you have large data sets, you have independent text data rows coming from the FASTQ data, and often batch processing is required. So we have seen some potential for MapReduce in genomics in 2010. So that was the first reason we started with Hadoop. And then we developed a graphical workflow system for Hadoop, and this is called CloudGene. And CloudGene allows us to execute MapReduce programs graphically. And of course, we want to push CloudGene. So we tried to implement more and more use cases based on Hadoop. Okay, so CloudGene, as I said, it's a graphical workflow system. You can execute your programs. And the nice thing is about CloudGene that you can combine different programs to powerful workflows. So when you have a MapReduce program written on the command line, you can integrate that into CloudGene by simply writing with the help of the interface a configuration file, and you can combine MapReduce programs. And we are working hard to also support other languages as well. So now with CloudGene, you can also integrate Apache Pig scripts. You can integrate R and also Unix command line programs into it. And all runs, of course, in your browser. And Lucas will give a talk about CloudGene tomorrow, and we also have a tutorial on that. So just a screenshot, a preview for tomorrow. This is CloudGene. We can integrate different applications into CloudGene. You can submit jobs. We have here a HDFS browser to import and export data. You can import data from different sources. You can import it from HTTP, from local file system, and also we also have an SFTP upload. And the SFTP upload has been developed here in Uppsala, and we integrated that into our CloudGene. And here you can get all the results, you can download things, stuff like that. Yes. Okay, so what kind of Hadoop pipelines did we develop in Innsbruck? So we started with pre-processing. We developed a FastQC. We developed a library which can be compared to the FastQC pre-processing library. We integrated snip test. We also developed a version of PWMM, which we integrated in CloudGene as well. But sometimes we use Hadoop not in the typical way. Sometimes HDFS and MapReduce is a bottleneck for us. So often we just use the Hadoop framework without extensive use of MapReduce or the HDFS file system. And I will show you in the next two slides what I mean with that. So for us, it's often the easiest way to use Hadoop. In combination with CloudGene and provide programs to our co-workers in our institute. And a really interesting use case we have been developed the last year is the imputation server. Maybe some of you know the imputation server. We have a cooperation with the University of Michigan, with Gonzalo Vicasis and Christian Fuchsberger. And they asked us if we want to integrate their imputation pipeline into CloudGene. And a second interesting project what we have in Innsbruck is the mtDNA server. That's a complete complete MapReduce-based pipeline for analyzing mtDNA data. So first of all, the imputation server. So imputation is a statistical method to boost the power of your GWAS, of your genome-wide association studies. And for that, you use your SNP panel as an input. So you have a VCF file, you upload this to the imputation server, and we impute this using the 1000 genome space-free reference panel. And this is done with Minimac. And Minimac is the algorithm we use for imputation. And this has been developed by Christian Fuchsberger and Gonzalo Avicasis in 2012. And the challenges for that is that's often the bottleneck in current GWAS studies, the imputation. Especially because of that the reference panel scales quadratically. And next year, there's coming an even larger panel coming out. It's called the Haplotype Reference Consortium panel, and this panel includes 35,000 sequenced people, samples. And this is a resource for imputation. And this is especially good for imputating rare variants. So the problem with this panel is that it cannot be distributed properly. And so you cannot download it like the 1000 genomes phase-free panel to your local worker, to your worker server and impute the data. And for that, we developed the imputation server. So we provide imputation as a service to everyone. And we adapted this complete workflow to Hadoop. We have quality control included, we have phasing included, and also imputation included. So here the easy picture is that here's the scientist, he uploads the VCF file to our imputation server, and he gets the imputed genotypes back. The workflow is a bit more complicated. We have a lot of quality controls included. The user can then download the report to the local workstation. Then we have phasing and imputation. Again, we have the HTML report with all the statistics which have been created during imputation. Then we have an encryption phase as well. So the data is encrypted with a random password, and then the user gets an email that he can download the data from our server. Behind this is the MapReduce workflow. So for quality control, we really use the MapReduce library as said in the beginning. So we chunk the file in the map phase, and then we create the statistics in the reducer. But for phasing and imputation, we don't use the MapReduce library. Here we just use a map-only approach, meaning that we're using the Hadoop framework for having different chunks, and these chunks are then automatically executed on the Hadoop cluster, but without using the MapReduce library. So here we only have a mapper, and we are using the so-called n-line input format for that. Okay, so this is the new CloudGene. It's a preview, it's not published yet. As you can see, we changed the graphical user interface now. We are now using the Twitter Bootstrap on client side. In the old CloudGene, we used the NGS framework. And this is the simple interface. So the user can simple upload the data via file upload from the local workstation or SFTP, and then the imputation is executed on our server. And also included in this new version of CloudGene is a real-time feedback. So the user sees, okay, what's the current status of my imputation? How many chromosomes are already imputed and finished? And yeah, the rest is pretty much the same as in the old interface. We get all the information back from our server. And we also have an admin panel. We have the possibility to go into maintenance mode. We can block the queue if we have to do any update on the imputation server. And we are pretty happy that this approach works really well. So right now, this is statistics from last weekend. we already imputed 350,000 full genomes, and these are the chromosomes. Yeah, they're not. And this is the current status of the server. So we always have a statistics how many people are currently imputing data on our imputation server. So of course you can try it out. Just Google it, the imputation server, or the web link is also in the slides as well. And the second service we are providing in Innsbruck is the MTNA pipeline. It's a more MapReduce-like framework, and in this workflow we start with FASTQ data. We do the alignment. We do also the pre-processing of the data. We give some statistics back to the user. We also count for heteroplasmies. We also detect the haplogroup. And for that, as I said before, we have here a parallelized version of the BWMEM algorithm included in this workflow. And this is hosted as a service at our university in Innsbruck. It's the MTNA server. And as you can see, again, this is the imputation server from the slide before, and we can just reuse the complete CloudGene workflow system and just integrate the new pipeline or the new workflow into CloudGene. And of course, we have different input fields here, and again, the user can upload data to it. And then he gets statistics about what we have done. As you can see, input validator here, we analyze the bound file, then we detect heteroplasmies, haplogroup detection, and also a contamination check. And as I said in the beginning, we not only provide MapReduce, we also provide our reports. So in this example, we create some nice statistics for the user, which you can simply download from MTDNA server as well. And of course, if you're not allowed to upload data to a remote server, we will provide this we provide CloudGene, of course, and the complete workflow will be available open source. So you can install everything on your local cluster. So we still see some potential for Hadoop in the area of NGS. And so we have two versions right now of CloudGene. CloudGene 1 is more a workflow system for your local institute. We have this HDFS browser. And then also, as you have seen in the imputation server or in the MTNA server, we also try to push it Hadoop as a service. Yes, and current developments are that we are working together with Enis Afghan. He's the man behind CloudMan. CloudMan helps you to set up a Galaxy cluster in the cloud. And currently, we are working together, and he tries to integrate CloudGene into CloudMan. So you can set up a cloud, for example, on OpenStack with CloudMan, and CloudGene gets automatically installed with the use case, for example, I just showed you. We also try to build workflows graphically. We have a new student at our institute who is working on that. And also the imputation server is under active development. And also we, as I said in the beginning, we are working together with Gonzalo Avicasis, and we are trying to provide their .cloud pipeline for SNP calling also inside of CloudGene. Yes, and yeah, the people behind CloudGene are Lucas and I, and I also want to thank our partners from Michigan and also our boss in Innsbruck. And this is our hometown, Innsbruck, and if you want to visit us, yeah, come for skiing. Thank you.
You mentioned that HDFS is getting a bottleneck. What other file system or distributed file system are you using?
Well, Carl, when either we are using HDFS file system or we're just using the Unix file system. So we are using external indexes, for example. Just, for example, Minimac has an index, so we don't split, for example, the file within the HDFS file system with the mapper or the reducer. So we just build different chunks. We use the Hadoop framework just to parallelize the jobs, and we just use external indexes on the normal Unix file system.
Yeah, last question, please. You mentioned about why bioinformaticians don't use Hadoop, and actually there is a reason for that. But this was in Hadoop, in Hadoop 1, I'm not sure about Hadoop 2. First is that it is very good for embarrassingly parallel jobs, but when you insert complex workflows, it becomes slow. And the second, the reason is when you process big data, when the data size become bigger, it becomes slow. So I'm not sure, I never used Hadoop 2, so these two problems are solved in Hadoop 2 using the Yarn scheduler?
Well, the nice thing about the new Hadoop 2 is that you have, as you said, we have in the Hadoop 1 we have just batch processing, and we have seen that as well in Innsbruck. Batch processing is not enough for processing NGS data, and with Hadoop 2 you have different processing models, and this is pretty much and well, we are working more with the MapReduce right now, but I think with Hadoop 2 you have a lot of more opportunities to build different workflows as well, not only batch processing.
So you tried this with big data?
Hmm?
You tried running workflows with
Yeah.
big data?
Yeah, of course. For example, the importation server is not, it's not small, so we have a lot of data for that. And also with the God Cloud pipeline, when analyzing BAM data, we think that even Hadoop is the better choice because you have the distributed file system. And we think that the NFS will be the bottleneck, not the computing. We think the NFS file system is the bottleneck when you get petabyte of data, of BAM data.